So now that we know how to use this Poincare-Lindsted method, which modifies our standard regular perturbation theory to account for frequency shifts, we have a much more powerful way to start to understand, especially oscillatory systems. And so one of the things I want to consider today, this is a classic problem of applied math, which is the forced Duffing oscillator. It's about as simple as problem you can get of a nonlinear oscillator being driven. So oftentimes, this is an example of a system. We're going to put damping in this as well, so a damp-driven system. And damp-driven systems exhibit all kinds of very interesting behaviors dynamically that we'd like to understand. And one of the ways that we understand those behaviors is not just through simulation, but through doing things like perturbation theory to understand the underlying structure driving that dynamics. And so we're going to consider this case today. And our main work tool for doing a lot of the analysis is going to be the Poincare-Lindsted method. So you're going to see this throughout as we go. So let's consider the pendulum. So the pendulum in the idealized case with no damping, you're not driving it, is just simply this differential equation here. It's nonlinear because you have the sine u. And so you have something that creates oscillatory behavior. But this is a strongly nonlinear system, especially if u becomes large, and sine u can be very far away from just a linear approximation of sine u is equal to u. So what we want to do, though, is start thinking about, as we start to make it nonlinear, what happens when we drive it and when we have damping. So let's start here. I want to start off with a forced pendulum. So I'm going to take that pendulum equation, but now I'm going to add damping to it. So this is going to be the damping term. So the damping term is just going to be some term proportional to u of t. In other words, it's something like proportional to the wind velocity or the velocity of the movement of that pendulum arm. So this is something trying to mimic what would happen, what we normally assume in physics as the coefficient of drag that would occur due to wind velocity is proportional to the velocity, and that's what this term is trying to model. So I have this damping term, and then I'm also having a driving term. It has an amplitude gamma and a frequency omega. And so you can see I already introduced three parameters here. Delta, which is the amount of damping, gamma, which is the amplitude of the forcing, and omega, which is the frequency of the forcing. And all these three terms play a big role in determining the eventual dynamics of this system. I also have some initial conditions. Here it is. Alpha and beta are the initial position and its velocity when you start the pendulum swing. And what I'd really like to understand is the kind of broad perspective of what kind of behaviors can come out of this system. So we're not going to work with sine u, because that's already, it's a tough problem. We're going to work in this limit here where we expand psi u, but we're not going to just take the linear approximation, which we often do in the pendulum, which is the linear approximation. And so this is where people often mistakenly know how they think they know how to solve the pendulum, is because they say sine u is u. And that's an easy problem. Start adding some nonlinearity to it, and it becomes a lot more interesting. And so what we're going to do is take a first correction to this. U cubed over 3 factorial. We're going to drop everything higher than that. So we're just going to try to understand what happens when I include this uq term in here. And in fact, when I introduce the u cubed in the oscillator, it becomes the Duffing equation. So now what we're really going to look at is this damp-driven Duffing equation, and to understand its dynamics. And I'm going to cover this in a series of analysis. And I'm going to start with the simplest case first and build our way up to understanding the full damp-driven Duffing equation. So here's the simplest approximation. No damping. I guess you could take away forcing too. But we're going to go ahead and just say no damping. So what I have is the oscillator plus a driving term, gamma cosine omega t. So we've often considered this in physics, and we talk about this as resonance forcing. And oftentimes we show, for instance, the Tacoma-Narrows bridge, and if you force a system at its resonance frequency, then amplitudes start to grow. And this is the prototype model for showing it. And in fact, this cosine omega t, if that omega is 1, in other words, at the resonance frequency, what that really tells you is cosine omega t. If omega is 1, it's actually sitting in the null space. And so it's going to generate secular growth This is exactly where you violate the solvability conditions, is when you start to generate this resonance growth conditions that make the solutions go to infinity. Which in this case is formally what happens, but in real systems, when you do a perturbation expansion, things aren't going to infinity. Most things are fairly well behaved, and you just want to understand what happens to the system, and so you're going to have to get rid of these secular growth terms. But for now, you can just simply solve this, and with the initial conditions from a start at rest, you'll get something like this. Your solution is t sine t. So it just starts to grow. Okay, there you go, with gamma being the forcing term. So in other words, the forcing term is adding energy to the system. So you're driving the system, and the amplitude and the oscillations start to grow. This is like being on a swing, right? When you start pumping your legs at the right frequencies, your amplitude of oscillation starts to grow, and there it is. Now, if you were pumping your legs on a linear swing, then your amplitude would go to infinity. And many of us tried, when we were kids, to make the amplitude of that swing go to infinity, and we never could do it. Not only did we have damping, but we actually had to deal with nonlinearity. And at some point, you get to a maximum height of your swing. And I don't know about you, but we had a swing set in our backyard when we were little. And when you got to really big swings, you kind of get the swing to come off the ground a little bit. We didn't ever kill ourselves, but that's when you knew to maybe stop swinging so hard, as if when that leg came off your swing leg came off the ground for more than a foot, then then you didn't want to really go to infinity on your swing, okay? But that's the idea here. And in fact, you're arrested typically with your swing due to nonlinearity, due to damping, and so we're going to talk about what that happens in this case realistically. All right, so that's the linear theory, and that had no damping, but it just had the driving. So I'm just pumping energy into that system, and what you do is if you pump energy in that system, you see the amplitudes just grow. So let's take this linear theory, though, and put damping there. So there's the damp, delta ut. So I'm going to solve this again. Now this is just a linear second-order differential equation, constant coefficient with an inhomogeneous term. And if you go back to your standard differential equation solves, what you end up doing with solutions like this, first of all, to get the homogeneous solutions, you plug in exponentials. Put those in, and then you find a particular solution which satisfied the right-hand side. And then you say my solution is the homogeneous solutions plus the inhomogeneous solutions. It's a standard way. This comes right out of something like Boyce and DePrima. That's what we do in that class, is solve up to problems like this. And there, the solution is given by here. There's two linearly independent solutions. Okay, here they are. All right, and if you start this thing again, leave from rest, what you find is the following solution. Here it is. So I'm not going to do the algebra of this problem because, well, I don't think it's necessary. But this is, in fact, the solution which accounts for the homogeneous, inhomogeneous solutions and starting from rest with those initial conditions. And here's your solution. And notice that I have a cosine omega t and sine omega t. And notice what happens here. This is the important term. I have a gamma, which is my forcing amplitude. So the amplitude of these solutions are proportional to what the amplitude of the forcing is, divided by 1 minus omega squared plus delta squared omega squared. Now, if delta goes to 0, in other words, if that damping goes to 0, this term drops out, and the bottom can be 0 when omega is 1. In other words, if the bottom is 0, then you're dividing by 0, this goes to infinity. But as soon as you have a little bit of damping, any small amount, notice it regularizes this. This can no longer be 0, because this is a squared of something plus this delta squared omega squared. So now what you've done is you went from having infinite amplitude solutions to finite amplitude solutions. And the difference here is you do have that damping, but the null space solutions for this, in other words, the homogeneous solutions, are no longer cosine omega t and sine omega t. In fact, they are this. These are the homogeneous solutions. So the right-hand side forcing is no longer now you satisfy Fredholm alternative. It's no longer in the null space. Okay? So now you get well-behaved solutions. Nobody's going to infinity. Okay, all because now solvability is satisfied. Okay, that right-hand side term, cosine omega t, does not span the null space. That's why this has finite. That's why there's no problem with the solution. Again, these are all linear, so this is just simple review, hopefully, of differential equations, second-order differential equations. Okay, and these are the kind of problems we actually solve in Boyce de Prima. And so now we want to move on to the more interesting cases. What does nonlinearity do? So let's start considering nonlinearity, because really that's what we want to focus in on this class, is nonlinearity makes the world a very interesting place to be. Nonlinearity is what drives all of this interesting physics that we often observed. If the world were linear, we'd all be bored. The world being nonlinear makes things really difficult, but very interesting, and generates all kinds of interesting behaviors. And so let's talk about what they are. So let's go back. I considered previously the linear case with no damping and with damping. Again, I'm driving this system. And I'm going to start thinking about driving the system, but now with a nonlinearity in it and no damping. So what does that nonlinearity do? I've already highlighted before that nonlinearity is going to shift frequencies, generate harmonics, and now you're going to drive it with this gamma cosine omega t. So somehow this is going to start to have an interplay with the processes that normally would be going on here, which is this generation of harmonics and frequency shifts. So we already talked about this previously. If we're going to have frequency shifts, our perturbation technique better account for it. So we're going to use this Poincare-Lindsted method. We're going to define a stretch time tau. Tau is omega t. And what we're going to do is expand omega. Omega is going to be a perturbation expansion, just like U is going to be a perturbation expansion. If you look back at the last lecture, that's exactly what we did. And when we did this expansions, at each order, we look at the right-hand side forcing term and say, what do I have to pick omega to be such that I satisfy the solvability conditions? Okay? So I put those all in. Here's my new equations. I went from the t representation to the tau representation. And normally what happens is UTT becomes omega squared U tau tau. I've divided by omega squared, and this is what you end up getting here. Okay, so I've just divided by the omega squared. And what I'm going to do now is start to actually define new variables here just for simplicity of the algebra. So if I rescale that, I have something that looks like this. U tau tau plus U, epsilon. And what I've done here is I've captured this epsilon parameter. I'm going to treat the forcing and the nonlinearity as perturbations to this problem. Okay? And that comes from back from here. So remember, I'm going to expand omega. So I'm going to get a correction here to this linear term. I'm going to get some correction term here, some term here. So all those terms that are approximations, I'm going to get one for the linear term, the cubic and the cosine, are now captured in these parameters, gamma and beta. And I've just set this to unity without loss of generality. Really what I'm just trying to highlight here is behavior, not so much, you can work out all the algebra. It's a lot of algebra, but it's fine to do. And I'm going to make this all perturbatively small. So my leading order solution is going to be here. It's going to be oscillations. And I'm going to ask, what's the effect of perturbative effect of having a driving, a nonlinearity, and this is the correction to the linear term here, where I can pick up my frequency shifts. Okay? So that's what I have as my solution. And then I can, so that was just the rescaled. And so now I expand. And when I expand, the leading order solution is right there. U naught tau tau plus U naught 0. Like I said, it's going to be just simply oscillations. And I want to understand what happens when I drive that and I have that cubic nonlinearity together. Can I understand fundamentally what are the interactions in this system and how does it affect the dynamics of this nonlinear oscillator? So the solution, of course, is going to be simple sines and cosines. There it is. Okay, so that's the leading order solution. And again, I've arbitrarily scaled the parameters so that this is true, right? So I've made it so that those terms are epsilon small. Okay, so I start there. That's my leading order solution. And now what I want to know is what happens to that solution as I expand this. Remember, the tau is omega t. So the tau, if I can solve for those different omegas, it's going to tell me how the frequencies of it are shifting. And then I want to understand also what's happening to the amplitude. Before, without the nonlinearity, I was really curious to see, does A grow to infinity or is it finite? And we had no damping, A went to infinity. With damping, A remained finite. What about the nonlinear case? Okay, well, here we go. We get the leading order solution. Here is the equations for the correction. So u1 tau tau plus u1. Here it is, gamma cosine tau minus beta u naught plus u naught cubed. And if you put in the leading order solutions into this, collect all the terms. And what are the terms I'm most interested in? The terms that live in the null space, the terms that are the null space. Here it is. I have a cosine tau term with all these coefficients. I have a sine tau term with all these coefficients. And then I have a cosine 3 tau, sine 3 tau. Now, I'm not worried about the cosine 3 tau, sine 3 tau, because they're not going to generate any kind of secular growth. They satisfy the solvability condition. However, that cosine tau and sine tau are going to be problematic. If they're not 0, if the coefficients are not 0, I will get a term that's t sine t. So it's going to be a secular growth term, which is completely fictitious. It's a property that it's just a result of the fact I didn't satisfy the solvability conditions. So I'm going to go satisfy solvability by setting this to 0 and this to 0. And remember, I have A and B I can play with. I have some of these other parameters as well, including the frequency shifts that I have, that allow me to set that to 0. And in fact, if you work out all the algebra, here's what you find. Here is essentially what the frequency has to be in order to make those secular terms disappear. Omega squared is 1 plus 3/4 kappa A squared minus gamma over A. A is the amplitude. Okay? Gamma, remember, is the strength of the forcing, and kappa is another normalized parameter. If you look at the notes that I have with the class, you can follow. I have more details in this, but some of this you just have to work it all out to see how all the terms pop out. This is a long calculation to get all this stuff to work out. Okay, so I'm not going to lie to you. So it's like you're going to spend hours working all this out if you do it. Okay. So what that allowed me to do then is figure out the frequency shift that happens when I force it with damping. Okay, and by doing that, I was able. You can generate a leading order solution. And you can generate its corrections. Okay, to that. I'm going to do one more term and then show a picture. I'm going to do one more case, sorry, and then show a picture. And this is going to be the full nonlinear theory with damping. So now I'm going to take that same case, and remember I didn't have damping before, and I'm going to throw damping on here. So there's the damping term. That's the only difference from before. Remember, gamma is how I'm driving it. Kappa is essentially the term in front of the nonlinearity. And remember, that's what I found here. Here's the frequency shift as a function of that term in front of the nonlinearity, as a function of the forcing amplitude, as a function of A, which is the amplitude of the solution. So this frequency shift all depends on how hard am I forcing it, how strong is that nonlinearity, how big is my solution A, which makes sense. But now with the nonlinear theory, I introduce one more parameter, which is delta, which is the damping term. So what I want to do with this damping term is see what happens now when I have a damped driven system. So I'm feeding energy in, and in fact, in the previous case, without damping, I could still get the solutions to blow up, but they blow up in a very different way than the linear case, and I'll show you that in a minute. So here, I'm going to drive it with the nonlinearity, with the damping. I'm going to do the same kind of Poincare-Lindsted expansion that I had before. So first, I'm going to rearrange things and rewrite it so that I can pull out a small parameter epsilon. So I'm going to treat, in fact, here, the forcing is going to be small, the nonlinearity is going to be small. This is a correction to the linear term here. And when I do the rescaling, and also I have here another parameter that comes, that's from the damping. So I've rescaled the damping. So there's the damping term right there. So my right-hand side now has the introduction of this damping term, which is this delta u tau. So what I'm going to do is do expansion again. So again, do your expansion. U is equal to U naught plus epsilon U1 plus epsilon squared U2. Take your frequencies, expand them, but now I'm doing it in this new variable set. I've reshuffled things for convenience so that my leading order solution is just cosine tau, sine tau. So the omega frequency is 1 is the base frequency. And do this expansion now in these new variables. Here are the results. When I expand, you do even more algebra. And what you're looking for is, at the next order, you look at the right-hand side terms, and you ask the question, which terms have a sine tau, which terms have a cosine tau? All the other harmonics don't matter. They satisfy solvability. But the ones with sine tau, cosine tau, those coefficients better be 0 in order for you to satisfy the solvability conditions. And you get that by having these relationships here. Here are your conditions that you have to satisfy for you to avoid having secular growth terms or to satisfy the Fredholm alternative. Okay? And so you can rewrite this where if you take a squared plus b squared as r squared, right? So that's one way to rewrite this. You see the a squared plus b squared pops up everywhere. You can do some algebra on this to simplify things down to a relationship that looks something like this. And along this curve, you've satisfied the solvability condition. So this gives you a way to sort of start to understand the kind of dynamics and the kind of what happens in this system as you drive it and as and it has this nonlinear term associated with it. So there was a lot of algebra here, and obviously I didn't go into detail. The main thing I wanted to highlight was what I used was this Poincare-Lindsted method to start to get to some understanding of this damp-driven behavior that is sort of common. Like if you drive an oscillatory system, what are the kind of dynamics that you get out? So this forced Duffing equation is a really important toy model which illustrates the kind of behaviors you're going to get if you take a system like this with this cubic nonlinearity and you drive it and it has damping. What are the behaviors? I want to finish this with a summary picture. These are your resonance curves associated with the 4 cases I just showed you. And what they highlight for you is the kind of behaviors you get out of the system. So in the first case here, this is the resonance curve typically associated with the one we learned in undergraduate physics. Like you drive a linear system at resonance, and what happens? Well, the amplitudes go to infinity if you're right at the resonance frequency. And that's what this is supposed to illustrate, right? So they always show you the picture of Gallup and Gurney, which is the Tacoma Narrows Bridge, right? It started being driven at resonance and things blow up. In fact, that bridge collapsed. So, of course, really the bridge was nonlinear and you had nonlinear effects, but the amplitude still got large enough to crack the bridge and break it. But this here is an interesting phenomenon. It's just sort of our first understanding of driving things at resonance. Now, if you were to take that same system and add just a little bit of damping, there are no solutions that go to infinity. In fact, here's what you get. These different curves represent different damping terms. So the less damping you have, the higher the amplitude you can produce. The more damping you have, the smaller the amplitude you can produce. Those are down here. So you go immediately from an infinite solution that it goes to, and this is just a consequence of the fact that now you're forcing this, and the null space is sitting on the right-hand side, so you don't satisfy solvability. So now you get the secular growth. As soon as you add a little bit of damping, the right-hand side is no longer in the null space, and finite amplitude solutions emerge. Now, what about if I have nonlinearity in this system? Well, that's what these 2 pictures on the bottom are. The first one here on the left is if I have nonlinearity and no damping. So I drive the system, so I'm putting energy into the system, and what it does is it takes this line here, which is what we had before, the resonance line, but as I drive this thing and the amplitude goes up, the frequency shifts. And we keep talking about this. And if you were to just keep changing your shifting frequency, you would just start riding up this curve. Okay? So it's not quite like this, where just here amplitudes go to infinity. Just like when you're swinging on a swing, if you're swinging on that swing, when you're in a very small amplitude, you're pumping your legs at a certain frequency. As your amplitudes get bigger, you shift your frequency of pumping that swing to match the frequency of oscillations. That's exactly what you're seeing here. Once nonlinearity is introduced, if you're going to keep it sort of resonantly tuned, you've got to keep shifting your forcing frequency in order for you to keep your amplitude growing. Once you add damping, this happens. You still have to shift it, but now your solutions simply are finite amplitude depending upon how much damping you have in the system. And again, low damping for this one, high damping for those over there. And so this gives you a very interesting characteristic behavior. So anytime you have dissipation in the system and driving in the system, there's a lot of behaviors that are represented by this kind of structure down here, which tells you a lot about the physics of what's going on in the system. And in fact, you can understand a great deal about this oscillating system by understanding that picture down there. And you can get all of this by doing this Poincare-Lindsted expansion, because it captures the most fundamental things you need, which is, as you drive this thing, you're taking this oscillatory system and the nonlinearity interacting in the system shifts frequency, creates harmonics, and you can keep shifting that frequency, but once you have damping too, you also have a finite amplitude that you're going to achieve in this. That's a maximum amplitude. So this is sort of just a highlight of this Duffing model. The Duffing model is one of these canonical physics models, which is it's one of the simplest models where we can understand the effects of damping, nonlinearity, and periodic driving of a system. And so because of that, it's such an important toy model to understand. And you can see just by playing around with the parameters, you get a really compelling viewpoint of the kind of behaviors you're going to get in these nonlinear systems. And you can get all these behaviors out just by doing these asymptotics and perturbation methods to understand this, versus just simulate it and see what you get. Right? I have something more here. I have a fundamental understanding of this by doing this Poincare-Lindsted expansion for these oscillatory models. So we're going to end there. And again, I'm going to highlight that Poincare-Lindsted is great when the underlying behavior is oscillatory. And what I'm going to cover next are methods where this Poincare-Lindsted breaks down. In other words, Poincare-Lindsted is not going to allow us to actually capture behavior that are transients and other things that grow and saturate, because that's not oscillatory. And so we're going to have to modify Poincare-Lindsted yet again to broaden our reach of where perturbation methods can go.